All right, good morning. How are you guys? Doing all right? Okay, so last time we left off, we had done this problem, or you guys had done this problem. I kind of threw you to the wolves, told you to try it, to see what you got, and I didn't give you a whole lot of time. So we're going to go through it today, kind of walk through it together to solve the problem, and then we'll launch into kind of the next step after sedimentation, which would be also before the second part of sedimentation, which is the coagulation and flocculation. So that's the plan for today. I have not yet posted a homework, but I plan to do so for you guys probably tonight. So be looking for that. It'll be on Moodle. Submission will be on Moodle, and I'll try to send you an email when I do that. And, essentially, I'll probably have it due the class period before our exam. We'll go through the problems. Might have some sort of in-class activity to give you a kind of in-class challenge to say, okay, I've seen these problems, now how about this one, kind of a thing. Okay, so with that, example 6.1, we had a drinking water treatment system. We were given some information. We've got some flow going into our circular clarifier, and really that flow is going to go kind of from the inside out, right? So it's going to be a system where we're pumping the water in, and then from the middle point, it's being pushed outwards. So perhaps the best depiction of that would be a cylinder. It probably does not have these dimensions, but we could have a radius or a diameter. We have some depth, or I guess I'll call it height. And we can then know something about our system. Okay, so that's all from the circular sedimentation basin. And we say the Q is 3 mgd. Convert that in a couple minutes. It gives the conversion factor there for us to cubic meters per second. Then it says after a storm occurs upstream, we often have particles and we're given a dimension. It says 0.01 millimeter silt particles. So when we see some length scale for particles, we're going to assume spherical, and then that would probably make the most sense if that was a diameter. Because the particles are this big. If you give some distance like that, unless you're specifying that's just the radius, we can sort of assume that the diameter of the particles then would be, we could say 1 times 10 to the negative, would that be, should be fifth meters, because it's 10 to the minus third, 2 decimal places even further, should be 1 times 10 to the minus fifth. Okay, we are also given that the density of the particles is 2.2 grams per centimeter cubed. We'll need to convert that into meters and kilograms, but I'll just go ahead and write that down for now. We're given that this depth, or the height, is 3.5 meters. So before I even start trying to solve the problem, you see what I'm doing? I'm just writing down the stuff as I find it. Oh, okay, this is that part, this is that part. Definitely recommend drawing a system out pretty much anytime you're able to. I find that to be exceptionally helpful and a great habit to have. And it's probably not a bad idea to see if you can go ahead and identify the different pieces of information and think about whether or not they're relevant for the problem. So you'll get problems sometimes that give you sort of a red herring, right? It's there, it catches your attention, but then perhaps it was useless, right? So just be thinking about, okay, what actually do you need for your problem as you go. All right, so we've got the depth, and we have a diameter for our clarifier at 21 meters, so definitely not drawn to scale. And the water is 15 degrees Celsius. And so with that, we know that we're dealing with this for the density, or excuse me, this for the density, and this for the dynamic viscosity, including the units. Okay. So, makes sense so far? Different pieces. All right. So, part A asks, what is the hydraulic retention time? That's our theta. We know that's V over Q, so that's how long water will spend in this basin. And so we are given a Q, so really we just need the volume. So here we need a little bit of geometry to say the volume is going to be equal to the height times the area. So that's going to be 3.5 meters times pi r squared. Okay, so pi r squared is the area of the circle for the cylinder, and that will be pi times, I'm just going to go ahead and divide 21, so it'll be 10.5 meters squared. Okay, so let's go ahead and just use Excel real quick. So we said 3.5 times pi times 10.5 squared. Okay, so the volume then should be 1,200 cubic meters. Assuming I did that correctly. We also have a flow rate, and that was given as 3 mgd, and we're going to go ahead and convert that using their conversion. It said 1 mgd is 0.0438 cubic meters per second. So if we think about it, going from million gallons per day to cubic meters per second. So days to seconds is a big mental jump, and then gallons to cubic meters is also a fairly big mental jump, although we can kind of relate it a little bit to maybe liters. You know, there's several liters in a gallon. I think it's like 4 point something or 3.7 or something. So in my brain, it's not super intuitive, like to like know if I did the calculation correctly one way or the other. But it gives us it right here, and we don't need to, you know, that's just something we could look up. At any rate, so we say 1 mgd for that many cubic meters per second. So if we take 3 mgd, we multiply that number by 3. So we could say equals 3 times that 0.4438 cubic meters per second. Okay, so then that means our theta should be V over Q. Once we both have them in meters, that would be 9,226 seconds. And that's the reason I've changed that from seconds to hours on our Kahoot on Tuesday was because 9,000 seconds doesn't mean a whole lot if you just say it, right? It's a little more intuitive to go ahead and say, okay, well, can I put that in minutes? 153 minutes. Even that, you know, it's helpful, not too hard to deal with, but it would just be even a little simpler to put that in hours. Your brain kind of has a better grasp of it, I would think. Mine does anyway. So that's where we got our 2.6 hours. We round that to 1 decimal place. Okay, so that would be our answer. So let's go ahead and say the volume was 1,212 cubic meters. The flow rate was simply 3 times that. Bless you. and then that means our theta was 2.56 hours. Okay, so no particular reason that we had to put it in hours. I just wanted to because it was, you can kind of mentally map, okay, how long is this water actually staying in there? It's like, oh, 2.5 hours. Okay. All right, so that's part A. Part B, any questions on that part? Any issues? Makes sense. Okay, so there was, in that, I guess there was some potential for forgetting or not recognizing how to think about the basin as a cylinder. So certainly that could be some trouble. Again, my recommendation is to draw it. Will probably help. Okay, so B is a little more technical. It says, will the clarifier remove all of the particles from the water? And we learned last time that the sedimentation velocity that we find needs to be less than or equal to that critical design velocity in order for all particles to be removed. Okay, so that's something we can check, is compare, okay, what is this system designed for? If we calculate V naught, given the parameters that we know, and compare that to a calculated sedimentation velocity that we calculate based on the particles, right? So this would be, like I said last time, this Vs is coming from particles based on the physics, and the V naught relates to the reactor. And typically for a sedimentation problem, at the end of the day, what we do is compare those two, comparing the particles to the reactor, and in some cases we're designing a reactor for a particular type of particle. Okay, so let's start with V naught. That's a little bit simpler. Critical settling velocity, we said this is Q over AB, area of our basin. We just calculated basically both of these, although for our area, I could have, we'll add it here, but I could have just kept this part without the 3.5, right? So I could have just started with the area. It would have been a little simpler. Okay, so our area then is pi r squared, pi times the 10.5 meters. Square that, so that should be 346 meters squared. In our Q, we also calculated essentially 0.13, we round it. This is 346. We of course want these in meters. So 346. So this way we have cubic meters on top, square meters on the bottom. Will cancel and give us just meters per second, which is exactly what we want for a velocity. So with that, I will, so part B, we have V naught equal to our Q, which is here, divided by the area of the basin. And if you remember when we were just introducing the whole concept of sedimentation, we were thinking about it conceptually, how many meters will a slow falling particle fall in a second? That'll be a very small portion, right? We said that's probably going to be 10 to the minus fourth or fifth or something like that. So 0.000 something looks pretty reasonable. Okay, so that would be 3.8 times 10 to the minus fourth, 3.7. Meters per second. So that actually looks pretty reasonable. It is a little on the quicker side if we're thinking about slow particles. I said fourth to minus fifth. So if we had something minus fifth, it was falling at that rate. We know that's not going to settle because this is the this basically says it has to go at least this fast, right? That's what our V naught is saying. Okay, so we take that. Does this make sense? Getting this part? So that's V naught. That's going to be helpful. It's not the full answer. So then we take our equation for Vs. This was our gravity times that difference in density, particle minus the water, times the diameter of the particle squared, divided by 18 times the viscosity. So we recognize, by the way, we had two different diameters. So that was another potential source of confusion if you're just thinking, oh, look, we have a diameter, the particle. I guess could have accidentally used that for your cylinder if you hadn't been thinking about it all the way, or vice versa. So make sure to keep that clear for these circular sedimentation basins. Okay, so this is the diameter of the particle. In this case, we said that's 1 times 10 to the minus fifth. So I'm going to go ahead and rewrite these. So acceleration due to gravity, that's 9.81 meters per second squared. Then multiply that by the density of the particle minus the density of the water. And I'll do the conversion, but we also have a shortcut. The shortcut is that in any kind of reasonable range, A, we know that the particle has to be more dense than the water in order for it to sink. And B, it's probably going to be kind of similar, right? It's not like we're dropping a little piece of lead and it's just going, right? So it's going to probably be in the range. So unless it's like some weird tricky, it's maybe worth double checking that it makes sense. But generally, you can take the number that's given and make sure it's approximately 1,000 or over 1,000, but basically 3 digits, and you're probably okay, right? Double check that I don't get creative and decide to do something tricky or whatever, but generally that's going to be true. So we kind of know this is going to be 2,200 once we convert, just simply because we know that the water here, if we fill that in, is 999.1. So in order for a particle to be able to settle, it has to be at least 1,000, essentially. And given that this is a reasonable problem, this is, by the way, this is kilograms per cubic meter. Given that this is, in fact, a reasonable problem, we sort of know this is going to be 2,200 kilograms per cubic meter minus that. To do that conversion, of course, we could do 2.2 grams per centimeter cubed. That would go to, if we just do the grams conversion first, 0.0022 kilograms per centimeter cubed. Then we need to cube that conversion from centimeters to meters. And so then we're going to end up multiplying by 1 over 100 cubed. So it'll be a multiplier by, multiply the top by 100 cubed, which will bring us back to that 2,200. I'm just going to clear out just a little bit of space for that. So 0.0022 kilograms per centimeter cubed times 100 centimeters, and I have to cube outside of the conversion per 1 meter cubed. Okay, so that should get us to cubic meters, and we see how that's essentially multiplying by 100 cubed. So that's following from there. Does that make sense? Okay. Okay, so we've got that part, and honestly, that's usually the trickiest conversion needed. There's room to make mistakes, but that's usually the tricky one. So in general, you can just assume that it's going to be on par with the water itself. Okay, then we take the dP squared. So that is 1 times 10 to the minus fifth meters square that. All of that divided by 18 times our dynamic viscosity, which was 1.139 times 10 to the minus third kilograms per meter second. Okay, so if you wanted to check all the units, you would find that they ultimately cancel out 2 meters per second, or they should. And remember this times 10 to the minus third, that's in the units themselves, so make sure to keep that for the dynamic viscosity. Easy way to be off by a factor of 1,000. Okay, so with that, we can crunch some numbers. Say Vs is going to be equal to 9.81 times, that was 2200 minus 999.1 times 10 to the negative fifth squared. All of that divided by 18 times, was it 1.139, I think? E to the minus third. If I did that right. 1.139, yeah. Okay, so I think I've got all of that in there correctly. And it is a value that's times 10 to the minus fifth. And so that looks pretty reasonable to me. And that's in meters per second. Okay, so I'm going to go ahead and write that out. 5.75 times 10 to the minus fifth meters per second. And that is definitely smaller than V naught. So that's where our answer came in, and we said no. They are not all removed. Maybe a few of them are removed. Okay. Any questions? Does that make sense, process-wise? Okay. Did you guys get part of that? How did you feel about it? Yeah, last time.
The first part was easy, but on the second part, I got confused with the conversion of the 2.2 grams per second.
Yeah, exactly. Yeah, so those conversions are. The nice thing is there's the easy assumption to make, right? But then we really have to remember the squaring or the cubing situation. Just start with like 1 meter, or how many centimeters per meter, or something like that, whatever's relevant, and then just put the brackets outside. It's annoying, and sometimes 100 cubed, you're like, wait a second, what's that number? But definitely, I find that way of doing it to make the most sense to me. Okay, so as I mentioned, that's essentially the primary sedimentation, or the basics of sedimentation in general. We might come back and talk a little bit about cases where we don't have discrete particles that are like free floating and not bothering each other during the sedimentation process, because we can't really use this the physics model for those cases if they're like starting to form like a sludgy blanket and they're all kind of touching each other. It's not going to settle in the same physics based manner, right? And so if we don't have that, we have to use some other methods. For now, I'm just going to set that aside and say there's other types of sedimentation. What we just talked about would be called type 1, but there's like type 2, type 3, type 4, whatever, to describe these different practical, like in practice, what happens. Are you having like what's called sweep, what is it, sweep? I don't know if it's sweep coagulation or sweep sedimentation. Anyway, sort of like all the particles start sticking together and sweeping through like as if you're sweeping out the particles. So it becomes a little more relevant, those types of things, when we add coagulants and then let them flocculate, because then we have a condition where particles are really wanting to stick together. In our case, we're going to stick with type 2 sedimentation even in this second part, and that does make some sense because it's like in the primary sedimentation we have little particles floating around, and then by adding the coagulant and doing the flocculation, then we're going to have these discrete particles now forming larger units of discrete particles. And if then we assume those are somehow perfectly spheres made up of other perfect spheres, which is, actually not too bad of an assumption. They're obviously not going to be perfect, but neither were the initial particles. Then we have those sedimenting, and we can treat them in that manner. So that's kind of what we're going to do, and it is a reasonable way to at least initiate a design process for a treatment operation. Okay, so when we stop and think about it, that last problem we talked about, we were dealing with particles of silt. So that's kind of like clay particles. And you don't want to be shipping clay through your pipes to your consumers, even if you were able to adequately disinfect everything that's hiding on those particles. You still wouldn't want to do it for a few reasons, because customers aren't going to want to drink clay. It just looks gross. Maybe they need minerals in their water, but probably not that much. Right? It is typically a hazard in terms of like the viruses and bacteria hiding in or on or around these particles. So, but even if you did do that, then you'd be filling your pipes with some sediment. That's not good either. So obvious reasons why we don't want silt particles to reach the end of our treatment train. And if we look back at that problem, we said we had 0.01 millimeter particles. That would be 10 micrometer particles, right? So if 1,000 micrometer, this is 1 millimeter, right? And so this would be 0.001 millimeters. So this was the particle range that we were talking about. And so if we look up here, we can see kind of different other particles in that range. And if we look at, there's a variety of these charts. And if they had a soil particle size, silt would be in this range, right? That would be clay particles. So this would be a particle that size would be on the very, very small end of what might be visible to the naked human eye. So not particularly visible, about as small or nearly as small as the diameter of the smallest human hairs, or the thinnest. So pollen, fog, algae. Some bacteria get about that big, but most of bacteria are smaller. And then we have some important cysts here. The cryptosporidium and giardia cysts are both kind of at most that size. So if you kind of think about for a moment that problem, we were trying to remove these silt particles, very important to remove. And if that system was challenged to remove those, well, it certainly also could not remove bacteria. It may be some of the algae, but not all of it. It would be removing maybe some of the giardia cysts, but probably missing the cryptosporidium. Even if it was designed to remove the 0.01 particles, right? But it wasn't even designed for that, right? And we saw that was a difference of a factor of like 10 almost or more. Okay, so that's kind of maybe interesting to think about, that like that design really was not made for that level of particle. You could definitely get sand particles, I would presume. If we think of a sand particle, like the tiniest thing you could see with the human eye compared to a sand grain, would make some comparison kind of like that, right? So, all right. So with that, what we want to do is cause the particles to stick together Particular because, or especially because if we take a look at our equation again, we had g times the rho of the particle minus the rho of the water, or I guess I'll write it this way, times diameter of the particle squared. And if you think about which parameters we can change, we could maybe change the viscosity if we change the temperature, but not by much, right? So this is almost nothing we can change on the bottom. Gravity, can't really change too much unless we invent artificial gravity or something. You could use a centrifuge to cause sedimentation. That's what centrifuges do, and we artificially elevate that acceleration term. So it's no longer gravity, but it's an acceleration. You can't really cause particles to be more dense usually. Small caveat, something called ballast. I'll talk about it a little bit in a few minutes. It's essentially when you're doing the coagulation, sometimes you add actual sand that's presumably going to get caught up with these larger particles. That could make it more dense, a cheap and easy way to make them more dense. Sometimes we do that. But even that, maybe not the best solution compared to if you look at the impact if you change the diameter of the particles. So if you get the particles to start sticking together, they're going to fall at a rate that's a squared proportion to their diameter. So it turns out, just based on the physics, if you make them larger, that's going to speed up their descent a lot more than anything else. Okay, and that also kind of explains why, if we think about, even just in our minds, thinking about, like, let's say, if you've ever played in a river or on a beach or something, and you think about muddy particles getting kicked up, some sediment stays floating for a long time, but if you kick up some sand, sand falls out really quickly, right? We might actually be able to intuit why, even if a sand grain is something like, I don't know, here or something, why that's so different than a silt particle here. Might be 10 times the size, but that's 100 times the speed at which it's going to fall. Okay, so how do we manipulate particles that would otherwise be kind of just free floating? And when I say free floating, that's in reference to, or I guess the technical name of that term for that would be particle stability. So when we say particles are stable, that means they're happily free floating and not sticking to one another spontaneously. So particle stability means like they're stable in solution, and it really does refer to sedimentation. Stable, I'll say stable against sticking together and dropping out of solution. Okay, so if that's our particle stability, there are some forces and some reasons why particles might be stable, and we need to understand those in order to understand how to destabilize them to cause them to drop out, stick together and drop out. So it's almost like we are trying to make particles bad influences on each other, and hang out with the wrong particles and drop out of their school, all in a group. Okay, so the force balances essentially that stabilize or destabilize particles that can repel or attract them. The biggest ones, or the kind of furthest reaching ones, are electrostatic repulsion. So a lot of times, if you do have particles, or really any surface, in contact with water, a lot of surfaces will have a charge. It's due to a variety of reasons. Sometimes it's acid-base chemistry on kind of organic or even inorganic endpoints. So, for example, some some molecule R might have an end group that has an OH on it, and that could be, you could consider a case where it loses the H or potentially even gains an H or something like that. That particular one might not be the most accurate, but you can imagine cases where you have positive or negative. Negative is more common because there aren't as many things that can actually do this or an equivalent, right? So this is probably not actually real, but anyway, you can have a positive or a minus charge. I'm just going to give it some sort of a X factor there. So don't get too confused on that. I'm just saying there are reasons why surfaces can have charges. So most of the time there'll be a negative, or chemistry will look different. Maybe it's OH minus, whatever. So they have a charge, oftentimes negative, and that charge will essentially reach out into solution and shield it from other particles. So electrostatic repulsion, we're going to say we've got a negative charge here and a negative charge here. There's some repulsion, right? That's going to be that charge taking effect to push one another away. If you do get something close enough, then you get a whole host of these shorter range attractive forces called van der Waals. If you ever have seen a little water bug floating on water because of surface tension, or maybe a little gecko climbing on like clean glass and it's like sticking its little sticky pads, those are actually both van der Waals interactions. They are on the sort of atomic range. So in the case of the gecko, its molecules on its little sticky pad are getting so close to the glass that there's these attractive forces. It's a little bit like a magnet. If you get close enough, one molecule to another, or one surface to another, they can attract each other, assuming they're not repelled by some electrostatic before that. So if you get them close enough, then they'll stick. In the case of the little water striders, bugs, it's actually the surface tension that's doing it, and that's the water molecules sticking together by van der Waals forces. It's providing some pressure upwards against the little guys' pads. Okay, so when we want to know something about these two systems, the electrostatic repulsion occurs, or it diminishes as a function of the distance away from your surface, and that's at it diminishes on a scale of, I think it's 1 over radius squared. So this is diminishes with distance. The van der Waals ones, it's, I believe, 1 over radius to the 4th, or maybe 6 for some of them. So that's why at a very close range, we get these van der Waals forces that can apply, and they're actually pretty strong. These are ones that would attract the particles together, but that drops off so quickly that normally the electrostatic will repel each other. So under most circumstances, if they're charged, the charge is going to just keep them at a distance, right? Okay, so one other feature of this electrostatic repulsion is the influence of ions in solution. So if we have water with any sort of ions, a little bit of electrolytes, a little bit of salt or whatever, there's an interesting phenomenon that's going to occur where positively charged ions will come and hang out next to the surface because they're attracted, thereby creating a secondary layer of charge here. After them, there's going to be, they're diffusing in and out, but generally they're happy to be nearby. They're actually going to attract a second layer of negatively charged ions. So we get this electrical double layer, as it's called, or EDL, where then we have some negative charges, still some positive charges around, but a loose layer of negatively charged ions, because it's just more favorable to have negatives around that layer of positive. And so what happens is that electrostatic interaction, the field itself does go at this range, but it also extends into solution, and then this layer of ions kind of extends its own field a little bit. So in this manner, we get this electrostatic repulsion that's keeping the other particles at arm's distance, so to speak. And a lot of times this distance, what we call this electrical double layer, is on the order of tens of nanometers. Okay, so this is something like 10 to 20 nanometers as just sort of maybe something that's somewhat typical from that one particle. And so then there's another 10 to 20 nanometers from the other particle where it's like, hey, no closer than this, kind of a thing. So they really are stable against each other in some cases. So when we stop and think about, okay, if these are the stabilizing forces and we want to try to get rid of those or mitigate them to get particles close enough so that they're magnetic to each other from the van der Waals stuff, then we can do something to disrupt this charge field. Okay, so if we put higher charged species in here, it will compress this electrical double layer because it's satisfied more quickly, it takes fewer ions. If there are fewer ions in solution in general, if we just have a few ions floating around, we're going to have a very diffuse layer here if it's very pure water, because osmotic pressure is pulling the ions, trying to keep them dispersed uniformly throughout solution. So this would be a low charge or low salt concentration case, and this would be a higher salt concentration case. And then if we start adding, instead of just a +1, if we add a +3 charge, it's going to satisfy 3 sections, 3 charges worth of charge on our surface and really shrink things. So we'll see that in a few slides. But this is really kind of one of the main premises of our coagulation. We choose a coagulant that can manipulate these charges and promote these van der Waals sticky forces. Okay, so just kind of another image, a little more cleanly drawn. So this is how we can think about it if we have some solid surface, and we would assume there's a negative charges all along here. Go ahead and use a different color. So we'd have negative charges on the surface. Then the first layer of ions that comes in is going to be those positively charged cations there. And then a second layer, and you see it's a little more diffuse here. Negatives, some positives are diffusing in and out. It's a looser layer, so this would be kind of that combination would be the double layer. Then we have out in the bulk liquid, meaning away from a surface. That's just generically what's out there. It's just some random mixture, right? So that's kind of a depiction of it, and you can consider what would happen if you were adding more or removing these ions. Okay, so let's take a look at a few graphs of what happens when you're adding some salt. So maybe it's sodium chloride, maybe it's calcium chloride. So if we were to add NaCl or CaCl2 or something like that, a lot of times we'll do Al2SO4. That's alum. So if we add something like that, and we're just measuring based on the cations here, in part because it's the cations that do the job right here, right? If we can satisfy all of those spaces with just one atom that's about the same size, or one ion, it's really going to have a shrinking impact. So we'll see that here when we take a look at these graphs that say, okay, what's the, in this case, we'll focus on this one first. What's the residual turbidity? So turbidity is going to be a good measure of particulate matter. At some point, I'll give you a better demonstration, but essentially, turbid water will scatter light, and so it's hard to see through it. That's different than stained water. So I could make my water here somewhat turbid just for a brief moment by creating lots of air bubbles, right? So if you tried to see through it right when it has all those bubbles, it's scattering light everywhere. There's no way you can see through it because light's just scattering everywhere. If I were to add tea to this, it would change the color, but assuming I didn't leave the tea leaves, like the particulate matter in there, I could filter it, and you can still see through it. I mean, even right now, it could look, you could think that, oh, it's blue in there, right? But it's the bottle that's blue, but you could dye it blue, and then you look through it, you could see through it, but everything looks a different color, right? That's not turbidity, that's just a stain. Turbidity is the actual particles that are going to scatter the light. So we can use that as a measurement to determine, okay, when have we coagulated our particles? When have they stuck together and fallen out of solution? So that's essentially this percent turbidity. That means at the top here, we're going along and it's like 100% turbidity, nothing has changed. It's got a whole bunch of particles in it. And if we look at adding sodium chloride, it goes, we're adding more coagulant. So all the way up to nearly 10,000 milligrams per liter of sodium chloride, and then it drops. Okay, so as soon as we have added 10,000 milligrams per liter or 10 grams per liter, then we get the drop off. So at some point, we have that drop in turbidity. That means we've added enough of the sodium chloride or sodium whatever to cause the coagulation to work. For calcium, we actually need 100 times less. I did that right. And so by the time we've added 100 milligrams per liter, we have added enough coagulant and everything has fallen out of solution. And that's very good news, because if we think about how much sodium chloride we'd have to add in order to use it as a coagulant, we're getting pretty close to salt water, right? Because seawater is typically something like 25 to 30 grams per liter of salt. Of course, that's going to be more than just sodium chloride, but there's a fair amount of sodium and chloride in salt water. So we don't want to add so much salt. It's kind of hard to remove salt from water anyway. We don't want to use sodium chloride for our coagulant. Okay, so for then calcium, 100 milligrams per liter, much more reasonable. That's still adding a lot of stuff and probably would be affecting the taste. And calcium will mineralize with a lot of different stuff, so probably not a good choice, but we can see that effect. Having the 2+ certainly made a big impact. And then aluminum here, which happens to be very easy to precipitate with some pH changes, is actually really nice, because that's going to be 10 milligrams per liter of our aluminum can give us our reduction. So it's very common to use aluminum, sometimes iron, Fe3+, as our coagulant, in part for this reason right here. We don't have to add a whole lot of it, and it's really easy to get our destabilization. There's a couple other ways we can look at this, these other smaller graphs here. If we take a look, the top one, this is potential. So this is kind of the charge, right? Or the strength of the electrical field out some distance away from a particle surface. Okay, so this is kind of how strong is that electrical field up towards the top. That's 100 millivolts. It's a very strong electrical field. So if we're thinking about the electrical field as a function of distance, this is distance here in nanometers, then we expect our coagulants to shrink that. That's the electrical double layer. So if we can cause that to shrink so that the distance is weaker and shorter, or some combination, then our coagulant can work based on the fact that they're no longer repelling each other, giving them the stiff arm, so to speak. So here we're just taking a look at sodium chloride, and 60 milligrams per liter, we end up with charge way up here. So let's say maybe we decide that, I don't know, 20 millivolts is enough to repel another particle. So we look there and say, okay, the particles are repelling each other at about 20 nanometers. Okay. If we have 600 milligrams per liter, that cuts it down to something like 8 nanometers. And then the 6,000 milligrams per liter here. And if you look at our chart over here, 6,000, if that's 1,000, 2, 3, 4, 5, 6, that's right around our range of, actually, I don't think there were 10. Anyway, somewhere in that area, that's right around the time where we're starting to get the destabilization, and we're under 5 nanometers. Okay, so that's, if we get less than 5 nanometers, looks like that's when we're starting to get our destabilization. In the case, if I'm right in saying the 20, this 20 mark was the one to look at. Okay, so that kind of gives us a good idea of what's happening. We can do the same thing, same type of plot, but instead use a constant amount of our coagulant. Maybe it's 50 milligrams per liter or something. +1 charge versus a +2 charge versus a +3 charge. With the same dose, we can see how those, just simply changing how charged the species is, changes that. And again, that's all because if we can satisfy this much charge with a smaller space, everything's going to compress more. It's all going to condense a lot stronger, not to mention any of the corresponding compression out there. Okay, does that make some sense? So on a strictly charge basis, we can compress that charge and get rid of the repulsion and impact by just changing the sorts of salts. Okay, so that brings us to ionic strength. Pretty simple chemistry term. Just a quick reminder, it's a measurement of how much charge is in solution. So we're going to need to do some calculations with ionic strength. We have the formula, ionic strength, or I. It's going to be in molar units of like kind of moles of charge per liter, essentially. It's going to be, our formula is 1/2 times the sum of the concentration of a given species times its charge squared for all species in solution. That's going to be molar concentration, so that needs to be molar concentration for the C there. So essentially, if we increase the ionic strength enough, we're going to decrease that electrical double layer and get our destabilization. So just as a quick reminder, let's do a problem here where we have magnesium chloride. It's going to dissociate to Mg2+ and 2Cl-. And if we dissolve 100 milligrams per liter of this, I'm going to ask you to find concentration of magnesium, chloride, and the resulting ionic strength. I'll get you the molecular weights here in a moment, or atomic weights. So Cl should be 35, 34.5, 35.5. I think it's 35.5 grams per mole. And magnesium should be 24.3. So I'm going to take this over here. Give you a minute to work on that. So it should just be kind of a review here, just a good opportunity to double check that you're comfortable with all this. guys got answers? Not quite. Okay. Give you another minute. Okay, so I'm going to go ahead and work it out with you here. So we've got magnesium chloride as essentially 2 chlorides, 35.5 grams per mole. Add that to the magnesium, we get 95.3 grams per mole for the essentially for the base molecule. We need that because we know we have 100 milligrams of that going to dissolve, and so that's 100 milligrams per liter is 0.1 grams per liter. We can then divide that by the molecular weight, 95.3. That should give us about 0.001 moles per liter. There's some decimal places there. I've got it in Excel I can show you in just a moment, but I'll just carry on for the moment. So that means for every 1 mole MgCl2, we saw, my mind's like immediately milligrams per liter. So for every 1 mole of MgCl2, we have 1 mole of magnesium and 2 moles of chloride, right? So in terms of our concentrations, 1 mole MgCl2 yields 1 mole Mg2 plus. So when we want to report our magnesium 2 plus concentration, that's going to be equal to whatever we found right here. So that's essentially 0.001-ish decimal places. If we leave it just like that, that would be 0.001 moles per liter. And then the chloride would just simply be 2 times that, because for every 1 molecule, again, we dissolve, we get 2 ions of Cl minus chloride. So that would be 0.002 moles per liter. And then our ionic strength would then be 1/2 times this Cl minus times -1 squared. So the squares always make it so that regardless of the charge, we have a positive outcome. Plus the Mg2 plus concentration times the 2 squared. And that's going to be our total solution there. I'll just quickly show you that in Excel. Let's do that. So here, I just kind of wrote the different parts out. Magnesium, got chloride, molecular weight of them both. Okay. That moles of magnesium chloride is 0.001 with some decimal places. So that means our moles per liter of Mg2 plus 0.00104, chloride 0.00209, and then the ionic strength comes out to be with that essentially that same equation, 0.5 times the chloride's charge squared is -1 squared is 1. So I just left it as just the chloride there. And then I went ahead and put 4 in for the +2 squared. So then 4 times that. So that comes out to be an ionic strength of 0.003. We'll just say 3.1. We can leave that in molar units. It's essentially moles of charge in solution. Okay. Does that make sense? Okay. Did you guys get that or get close enough? Not quite. Where'd you diverge?
I did not do that. I did 100 milligrams per liter. I forgot, to be honest, though, so I just guessed. But I did 100 milligrams per liter, changed it to grams, and then multiplied by like the 24 for the Mg and then the 35.
Right.
And then I multiplied by 2 for the Cl.
Right.
Stoichiometry.
Yeah. That makes sense. Yeah. Well, and this is exactly why I wanted to go ahead and do this and walk it through, because if it's been a few semesters since Gen Chem or whatever, or if since you've done a lab, that's exactly right. So you have the solid essentially that we're dissolving, and since that's our starting point, we have to work from there. But I mean, it sounds like you have the right process. Just you started from the wrong spot, kind of. Okay. If you'd like some more practice, here's another one. It gets slightly more complicated here, and sometimes I do this to remind you that, okay, in this case, we have the same stuff we just saw going into solution. Right? But we also have sodium chloride adding sodium and some more chloride. The deal here is, and I'm pointing this out for exactly the same reason as we just talked about, this would give you 2 terms for Cl minus, and if you're if it's been a while again since the thinking about chemistry problems, what you need to do here is just simply add the 2, right? You're not going to have in your ionic strength equation, it's going to look like this, we'll say. Cl minus times -1 squared plus Na plus times 1 squared plus our Mg times 2 squared. That's going to be the total equation, and you notice I just have one time where we have the Cl minus. So we don't have 2 different Cl minuses here. We need to calculate the total concentration of Cl minus, right? So just because we add it in 2 different forms doesn't change its concentration. So just keep that in mind if when you do that one. Okay, kind of moving on to the last little bit for today. Once we add a coagulant, and I think I'll probably come back to describe a few more coagulants because sometimes we can use other tricks. I mentioned adding ballast like sand to add some density while we're getting them to stick together. You can also use some polymers to reach in and satisfy a charge and then sort of like do a bridging sort of thing where the polymer is like grabbing that particle and attaching it to other particles with a different arm. So there's different ways we can increase that. But for the basics, for using any type of coagulant, if we are causing the particles to stick together, then we want to start looking at the flocculation side of things. Well, what's happening and how do we deal with that mathematically? So I just want to scratch the surface of it today. We will pick up in flocculation next time. But essentially, we're going to give them gentle mixing. So whereas when we're adding the coagulant, we just need it to get all mixed up. So we use a very small chamber, very highly mixed. It's just we're injecting coagulant, mixing it all up real quick. Then we put it in a slower chamber so that we get no turbulence because we don't want to break apart our particles. We just want to let them collide. So some mixing, but not violent mixing, essentially. So we want particles to be able to stick together without breaking them back apart. And we want to reduce N is the concentration of particles. So this would be like particles per liter or something like that, right? Per volume. Maybe it's cubic meters, whatever it is. This is a number concentration. So we want to reduce the total number of particles in solution because they're sticking together, becoming fewer, larger particles, right? So if we want, and actually the picture down there shows it pretty well. If we have a whole bunch of particles, we want them, that would be 6 particles, and now we have 1 particle made up of 6 of the former ones. So this is N decreasing over time. That's the picture of it, right? We're not losing any mass or anything. We're just sticking them together and calling them now, what used to be 6 is now 1. Okay. Now, the rate at which that happens, the rate constant for N changing, because we want some sort of a dN dt, should be a decay reaction, right? It's going to depend on how many particles are in there, first of all. So we know it's going to be first order, just on the principle of the particles have to collide together, right? So the rate at which they're going to collide together will, if you just had 2 particles in my water bottle, gently mixing, how often are they going to meet each other? Not very. It depends on how many are in there, right? So it will depend on that, so it will be first order. And then there's some other factors that I will get into next time in depth. But for the moment, we really just want to think about the mixing intensity. This is called G. This is essentially a gradient of how fast water is moving next to a surface. So if this is a surface, particle or side of a basin or something, and we have velocity here, I'm drawing this probably backwards. We'll do this. Let's say we have little velocity terms going this way, starting from kind of that same spot. We see that until we reach kind of the velocity in solution generally, that gradient here, we'll call this our mixing intensity. Because if this would be essentially dy dx, so that's the rate at which the velocity changes, or I guess maybe dv over dy might make more sense. Don't worry too much about it. What I'm meaning is that this is g. That's the rate at which our velocity is changing as we get further away from an edge. So if we have a paddle mixing the water, how quickly it's moving next to the paddle, it's because of the force of drag, it's going to be lower next to it. and higher later. So the steeper, the sharper the thing, that's the faster, that's more intense mixing. Whereas if it's just about the same anyway, it's pretty slow mixing. There's not much of a gradient there. So anyway, we'll pick up there. We'll talk more about that and then start doing the math in terms of what all goes into that rate at which they're going to stick together. And that'll be our flocculation. Any questions? All right, thank you. And just a quick reminder, I know that some people have made use of attendance online. I'm glad to be able to do that, especially when there's people sick. I do expect you to kind of let me know what's going on, so thank you for those of you who have. Otherwise, I am expecting you in person, so just let me know if there's some issue that's why you're not here. All right, see you guys on Tuesday next week, and I'll get a homework posted for you before that.